Okay, let's take a look at lesson 5.4, quick review and a couple of examples to look at here too. So lesson 5.4 just is an application of our integration, definite integrals. So we look at a few things here. One is what we call the net change theorem. And then the other one is we use that to calculate a displacement. Displacement means, again, the total, not the total distance an object travels, but where it ends up with regard to its starting place. Okay, and again, that becomes a science term, displacement, you may have encountered in chemistry, physics, maybe even biology. And so let's look at that real quick. And you have this example here, and I'm not too worried about the formula per se. You can take a look at that. It is a variation of our original formula, but what we're doing is we're applying the integration to actually some physical situation. And so in this case, this first one, we look at what's called displacement and total distance. And so you have this example that's already completed, example 5.2, 5.24, 5.25. I'm going to do 5.22 for us, the checkpoint, but want to make sure, again, you understand the difference between those, this net displacement. Where does the particle end up, or where is it? If I know its velocity function, how do I know where it ends up from its original place, right? After a certain amount of time, how far am I from the original place? So you just integrate that velocity function over the interval that we're looking for from 0 to 3. Now, total distance traveled, we end up with a different situation where we have to calculate the absolute value of the velocity, right? The absolute value of velocity from 0 to 3, absolute value, and you see that we end up, and the reason is if you look back to this graph here, this velocity equation is negative down here. So that means the particle's moving in an opposite direction. It's moving in a different direction as it goes from negative to positive. It changes direction right there. And so you'll see the reason why we have to find its intercept and then integrate over those two intervals, the opposite, but it has to do with this absolute value. So that's what I want to look at real quick. And then we'll look at this section ends on integrating even and odd functions. And it has to do with the symmetry of those graphs and what happens. So let's take a look at 5.2 as an example for you. So first, we're going to calculate the net displacement and the total distance traveled. That'll be the second over the interval 0 to 2. Here's a graph of that. So you can see it's negative from 0 to 1.386 and from 1.386 to 2. It's positive. So you can see the velocity, the particle changes direction. So to calculate the net distance, the first thing we need to do is, again, where does the particle end up? You're just going to integrate from 0 to 3 of that function. Here is the integral, right? The integral of e to the t is e to the t. And so it turns out, remember, this here is the derivative of this would equal this here. So you can see, or this is what's the antiderivative of this. And then we're going to evaluate that from 0 to 3. And so when we do that, you get 1/2 e to the t minus 2t is the integral of this. And then you substitute 3 and 0 and calculate. And then you get this, again, because we have e's and natural logs potentially, I leave it in exact form, 1/2 e cubed, 1/2 times e cubed minus 13. So you have that there. That becomes its displacement. That's where, again, we can get that as an exact value, and that would be its displacement, where it ends up with respect to its starting location. Now, this next question of distance traveled, velocity, right? We have the velocity function. Total distance is going to be the integral from 0 to 3 of 1/2 e to the t minus 2. So you can see we have an intercept of change of direction at natural log of 4. So I solve for its intercept here, 1.386, or natural log of 4. I'm going to use that as its value. And then notice, again, because from 0 to 1.386, I'm in the negative region. I do the opposite to calculate the area, right? I'm trying to find the area underneath the curve. That's our application. And so I want the total distance. I just want the positive part, hence the absolute value. And then we just go ahead, and it gets kind of ugly, kind of hairy here. I double check the calculations. I think I'm right. So you can take a look and pause and look at my calculations. You have to evaluate twice, right? And then you end up with all these, and you substitute natural log into e. Remember, those are inverse functions, right? 1/2 times natural e to the natural log of 4 is 4. And so that's where you end up with that 1/2 times 4 should be a little times there, right? 1/2 times 4 right here is your 2 here. So with all that simplified, this would be your total distance traveled. Now I'm going to show you, I'm going to send you a link to this Desmos little website here, the graphing calculator, where you can plug in a function and you can at least check your answers. So you can see using this absolute value 1/2 e to the x minus 2, there's the graph of the absolute value, right? And then this is what I ended up with right here. So you can see I ended up with this here equals 6.08, which is the same thing that you get when you integrate here. So I'll include that link there for you, so you can check to see what we have there. Now, this section ends on odd and even functions, so you can pause and take a look at 2 other examples completed. But notice again, once we have an even function, there's symmetry on both sides of the curve. And since I'm integrating from -2 to 2, we have, you can do it from 0 to 2 and then just multiply by 2 to get your answer. It's just a shortcut way. And then if we have an odd function, which this is an odd function, which means that you have the sides are opposite of each other on the left side of the y-intercept and the right side. So you can see, because I'm integrating over the same values, it does simplify to 0 because of the total. One's negative, one's positive. Again, just keep that in mind in some situations where later on we'll have to break up integrals, and we have functions that are even or odd. That will be it for this section.